dobrý den, mé jméno je Michael, jsem chemik pracující na Ústav anorganické chemie Akademie věd České republiky. A jak slyšíte, trošku česky umím, ale asi pro mě je to určitě lepší. Lepší by bylo pro mě v angličtině. Si myslím, že by bylo lepší i pro vás v angličtině, ale to dávám na vybranou. Může to být na dobrou angličtinu nebo taková špatná čeština. Tak Luciana může pro tu lepší český a anglický variant. A v češtině? OK, takže dám trošku anglicky, trošku česky. Rozumíte alespoň trošku anglicky? No, tak vidíte. Do you recognize this boat, this ship? It's the Titanic. If you look very carefully here, you'll see Jack and Rose, who are in love. They still don't know what is about to happen to them, but the reason why I begin with this picture of the Titanic was that the Titanic sank in the year 1912, so just over 112 years ago. And 1912 is a really important year for me, because in 1912, Alfred Stock, a German chemist, synthesized the first boron hydrides. And the boron hydrides are a group of compounds that I've devoted my career to studying and using. And so I'm going to be speaking about these boron hydrides and why they are important to me and to our lab and to hopefully to you as well. But allow me to put into context the whole of whether it be boron hydride chemistry or any hydride chemistry into a universal context. Okay. Because really, in the entire universe, there is only one struggle, one problem to be solved, and that is the problem of entropy. Now, entropy is the universal fact or force which is degrading everything in front of our eyes. It's a law that says where there was once complexity, there must be simplicity. So complex, složité věci musí nutně, rozumíme si. They have to fall to pieces and become simpler. And the fight against entropy is a fight which, as much as we know and understand, is only partially won here on our planet. It's extremely difficult to roll back entropy. Now, entropy is the reason, for example, why this egg will break. And the reason is because there are many millions and billions of states in which the egg is broken, and yet only one state in which the egg is whole. And because of that fact, the egg will eventually break. We know that, and that's because of entropy, or the second law, which states that entropy must increase, or at least stay the same. Okay? So everywhere in the universe, all that is complex is being forced to become simpler. Everything's forced to break down, to degrade, to rot, including of course us. And it is important to note that entropy is a one-way system. Okay, yesterday was yesterday, today is today, tomorrow is tomorrow. We have a direction. That direction is due to entropy. We often think of it as time, but really what it is entropy. It's the course of things, the flow of things from complex to simpler, and of course it also affects us personally. We are every day battling against entropy, which is trying to turn us back into very simple molecules like carbon dioxide and methane and ammonia and the rest of it. So, how does our planet do it? How can our planet take the fight to entropy? How can it sort of reverse the progress of time, as it were? What it does is it uses chemistry. And it uses chemistry in, as far as we know at the moment, in a unique way and in a way of genius. This is a periodic table of the most common elements we find on the surface of our planet. Now, the size of the box of which the element is shown is representative of the amount of the element we find on the surface. And as you can see, it's dominated by 3 elements: carbon, oxygen, and hydrogen. And it's no surprise that you are all mainly carbon, hydrogen, and oxygen. You're about 60% oxygen, 20% hydrogen, 20% carbon. The table here is of a similar ratio of elements. Our planet uses these 3 elements to win a fight, at least partially, against entropy. And it does it using the genius of photosynthesis. So to reverse entropy, we need a source of energy, and that source of energy is the sun. And photosynthesis can take simple molecules and convert them into much more complex molecules, reversing entropy using sunlight. So it takes molecules of carbon dioxide and water. So for me, carbon dioxide and water are they're quite tired molecules. They're a thermodynamic minimum. They don't necessarily feel they have to show the world what's in them anymore. They're there for the quiet life. They're very stable. They're very happy as they are. Photosynthesis takes 6 molecules of carbon dioxide, 6 molecules of water, and using the energy of the sun, reverses time, reverses entropy, and introduces molecular complexity in sugars by making glucose. Okay? Look at the number of atoms in this molecule. 6, 12, 18, 24. So a much larger number of atoms in any particular molecule. The complexity's gone up, right? So entropy's gone down. And oxygen, of course, which is the remarkably reactive, neodolapelna kyslík, which will react with almost anything. So once photosynthesis, this ostensibly simple chemical reaction, which reverses entropy and creates chemical complexity in the form of sugars, once we have this, and we have a lot of time, then our planet can do organic chemistry. Because these complex molecules contain within them trapped sunlight. The energy is maintained, it's converted from photons of light into electrons. The energy is maintained, it's not lost, it's encapsulated in these complex molecules. Of course, that energy then wants to be redistributed according to entropy. And it does that by doing all sorts of wonderful chemistry, making new chemicals. So for example, this one here, I'm going to just show you some of my favourites. Do you recognise this molecule? All of you are using it now. Does anybody want to tell me the name of the molecule? That's right, it's hemoglobin. So this is an organic ring, and in the centre is a single atom of iron. And this molecule can grab from the air an oxygen molecule and deliver it to wherever we need it inside our body. Incredibly useful molecule. If we extend one of the chains onto this heme ring and replace the iron for a magnesium atom, we form this incredible molecule, one of the most important that we have. Does anybody recognise it? That's right, chlorophyll. So this is the molecule that really helps that moment of natural genius that converts a photon of light energy into an electron. So it's the molecule that enables, facilitates the storage of light as chemical energy. Do you recognise this? Any guesses?
Dopamine.
Sorry?
Dopamine.
Dopamine? No. Dopamine's a lot smaller. But you're sort of on a good track. So this is a molecule of oxytocin. Now, oxytocin is, we all generate oxytocin, but females maybe 8 or 10 times the amount. And ladies, this is the molecule which enables you to love your husband or partner, despite all their complications. So, we like to think we are a romantic species and believe it's a question of the heart, but really it's chemistry. So it's molecules such as these which enable us to feel emotions such as attachment and love and loyalty. These are all coming down to complex molecules which are formed naturally once photosynthesis has enabled the reversal of entropy and the formation of complexity on this planet. Now, this concept of which I've spoken was really the brainchild of this Nobel Prize winning chemist, Emil Fischer. And he got his Nobel Prize for working out the molecular structures of lots of important organic materials, caffeine and theobromine in chocolate and the rest of it. And when he received his Nobel lecture, he said the following. He was talking about photosynthesis, as I have just done. And he said, "The superb natural process without which the living world could not exist, i.e. the assimilation of carbon dioxide from the atmosphere by plants, seems even more interesting. This leads, as we know, to the formation of sugar, nature's first organ."
I would propose some experiment. I believe you're speaking quite loudly, maybe without the mic. Maybe you're there just...
Further, can you hear me? Is that okay? Is it better with the microphone? Is that better? Okay. So, let me continue. This leads, as we know, to the formation of sugar, as I pointed out, from that complex molecule, nature's first organochemical product from which all other constituents of the plant and the animal body are formed. That's the point. He realized that the simplicity that runs through there, we have the process of photosynthesis which converts light energy into chemical energy, can reverse entropy, formulate complexity, chemical complexity in the form of sugars, and from these sugars, all the rest of it develops. But he continued. And so progressively, the veil behind which nature has so carefully concealed her secrets is being lifted where the carbohydrates are concerned. Because this simple principle really is a powerful one and can explain all the complexity and diversity we have around us. However, it is increasingly obvious that the one-sided study of carbon compounds cannot suffice to elucidate the nature of chemical processes in all its aspects. So, our planet has chosen carbon to do its chemistry. We are possibly the most advanced, sophisticated product of this organic chemistry that has evolved on our planet. However, his last point is fascinating. So carbon's been chosen here, but there's all these other elements. What about them? can they do something? Can they produce something? Don't forget, we have photosynthesis, which is based on the chemistry of carbon, taking an oxide of carbon and making a hydride of carbon. But what about other elements? Listening to his Nobel talk was his best student and my favourite chemist, Alfred Stock. And Alfred Stock thought about that, well, that's a good idea. An idea maybe worthy of investigation. What about boron? What could boron do? Because boron is next to carbon in the periodic table. It just has one electron fewer than carbon. So what about boron? What can boron do? Of course, boron doesn't have, we don't have a photosynthesis for boron on the planet. It meant that Alfred Stock had to develop the synthetic techniques in his laboratories to make them. After finishing his PhD with Emil Fischer in Berlin, he spent some time in Paris, working with a professor there who was particularly advanced in using new laboratory methods and techniques that allowed water-sensitive and air-sensitive chemistries. He then took a place not far from here in today's Wrocław, but it was at the time Břeclav. It was at the time still part of Germany, now it's part of Poland. Recommend going to visit, it's a lovely place. And he got a place there, and in 1912, the same year as the Titanic was sunk, he made the first boron hydrides. And here are some sketches of them. Now, this is where it gets beautiful. Here, I'd like you to compare. I think beauty is important in science, and it is very much fun and something which can be enjoyed by the scientists taking part. Here are typical structures of hydrocarbons. They are composed of chains and rings. They're usually flat or staggered. And here are the boron hydrides that Alfred Stock first synthesized. And you can see they form rather different structures. They're similar in overall size, but they form three-dimensional assemblies that we call clusters. And the reason is because carbon is electron precise. That means it's got 4 bonding orbitals, valence orbitals, and 4 bonding electrons. Whereas boron has got the same number of bonding orbitals, but only 3, not 4, 1 electron less in its bonding valence. This means that the chemistry of boron is all about its desire for electron density. And it satisfies that desire when it bonds with itself by forming these 3-dimensional cluster compounds. In the same way as if all of us were to jump into the sea and go snorkeling, or go scuba diving, that we could survive with fewer oxygen tanks than people if we shared our oxygen tanks with us. So and we can only achieve that if we cluster together and stay in close proximity. So these beautiful 3-dimensional boron hydride clusters came onto the scene in 1912 with a big bang. Because at the same time, of course, thanks to the work of his PhD supervisor and Nobel laureate, the diversity of organic chemistry had become apparent. And these boron hydrides were the first example of something outside of carbon chemistry that had all this complexity and diversity and availabilities. Later on, these two chaps, this is a picture I actually took when I was doing my PhD in Leeds. We were in the pub, and this is Ken Wade, who's an Englishman, and Robert Williams, an American, and they came up with the Wade and Williams rules, which classify the boron hydrides into categories. And these categories are based on their geometry and on the number of electrons per molecule. So you have what's called the closoboranes. These are based on closed polyhedra. Nidoboranes, from the Greek for nest, which is based on a closed polyhedron minus one vertex, so it's slightly open. And then arachno, where there's two vertices removed from the closed polyhedron, right? So for example, if you start with an 11 vertex closed polyhedron, you remove one vertex, you get a nido 10, a nido 11. If you remove another two, then you get to the arachno. Now, when you look at the number of bonding electrons, then as the cluster opens, it has more electrons, or perhaps a better way to explain it is as you input further electrons, the cluster will open. As its electron density increases, it will open up. So, after the discoveries in 1912, there were several pieces of work which looked to both explain the bonding, the stoichiometries of these compounds. They began to discover lots of different examples. They began to categorize these molecules into structural patterns. And around this time, it became, if I'm looking now at sort of the late 50s, early 60s, the Czech Republic, or Czechoslovakia, began to play a key role in the development of this boron hydride chemistry. And it was to do with top secret projects which were set up for the first use of these molecules. So the first use of the boron hydrides was as rocket fuels. And that research was top secret. This is the laboratories are based in, just around the corner here is Rzesz u Prahy. So this is the way to, this is Rzesz Husinec, Rostoki, and then you're going upriver to Prague, and then there's Rzesz, and then downriver to Kralupy. And hidden away there are some top secret research laboratories, and you had fantastic people working, like one of my heroes, unfortunately he died a few years ago, Jaromír Plešek, some great chemists from this Czechoslovakian group who, under top secret working conditions, really did a lot of development of these boron hydrides. And once the work became declassified, they organized the first ever international conference in the area, which they held at Liplice, Zámek. Have you ever been to Liplice? Recommend it. It belongs to the Academy of Sciences. It's really good for a romantic weekend. And so this was the first ever boron hydride international conference. There's a couple of Nobel laureates in there, and it brought together from both sides of the Iron Curtain this American group working on top secret rocket fuels, and this Czechoslovakian group working on top secret Russians, and all sorts of. So it really sort of brought everybody together. With this, Rzesz and our institute became a key player in boron hydride chemistry globally. So if I put this into a timeline, if you remember, Alfred Stock discovered the first boron, or synthesized the first boron hydrides in 1912. Then from about 1941 to 1965 was this era of top secret research where they were looking to use the boron hydrides as rocket fuels. Don't forget, the boron hydrides, the same as the carbon hydrides, love oxygen and they will burn in oxygen. The boron hydrides actually burn with a greater ramp heat, so they release their energy faster than the carbon hydrides. They give a beautiful green flame. In fact, till today, if you look very carefully, I don't know, at Elon Musk's rocket launches, right at the beginning you'll see a bit of green flame, and that's due to it starts off often with a bit of boron hydride fuel. However, rocket fuel has been replaced by hydrogen and oxygen as a far more superior alternative. But there was that period of rocket fuel research work, which was very exciting. There were spies coming to Prague, trying to get to Rzeszów to find out how the scientists here were getting on, and there were top secret demonstrations in Rzeszów by the river to these delegations from Moscow to show how the rocket fuels were coming on. So very exciting. However, as a chemist, as somebody who considers these molecules as my babies, to see them just being burnt, to see them just being oxidized is a big shame. So I'm very happy that since declassification of the research work in 1965, our institute here in the Czech Republic is responsible for various key developments on how to use these compounds. So we've been making, we've made a huge portfolio of new boron hydride compounds, and we've also now developing their uses in areas such as, this is for example the extraction of radionuclides using the compounds. There's use in medicine, for example. So this is a structure of an enzyme called HIV. This is an HIV viral enzyme which is used to cut up DNA strands once the HIV virus infects the cell, and it begins to use the DNA apparatus of the cell to reproduce its own genetic material, and then it's got an enzyme which cuts it in the right place. These compounds of ours will fit into these enzymes and stop their action. So there's all sorts of interesting medicinal possibilities, based also on the fact that viruses, bacteria have developed and evolved to be used to organic chemistry, and boron hydride chemistry, although the molecules are very similar in size, they present new challenges for bacteria and virus. So there's all sorts of fascinating chemistry there. There's lovely chemistry coming from our institute looking at modifying the surfaces of metals using these clusters. But I'm going to speak a bit about microelectronics, where I started, and then on the use of these compounds as a laser material, as a material to form light, and then our current project, which is a European project, where we're looking to develop a brand new form of boron-proton fusion for the very clean production of electricity. Right. Okay, so that's a sort of introduction to and a context about boron hydrides. Now I'm going to tell you, I'm going to try to give you a few sort of pointers about how the chemistry works. This is decaborane, right, which is B10H14, NEBEC, right? The green balls are atoms of boron, and the white balls are atoms of hydrogen. Okay. Now, the reason why I'm talking about this particular molecule is this is a kind of molecule you can actually buy. So you can get from various suppliers around the world decaborane. Some notes about its chemistry. You can see there's an open face. Here's like an open face of the decaborane cluster. Well, and so it's like a sort of a bowl or a dish or a bucket. And indeed, the electron density within this bucket goes to the bottom of the molecule. So here are sites where I can achieve electrophilic substitution reactions. So here I can do reactions with reagents that are looking for electrons. And on the opposite is true. These two sites here have got little electron density. They're looking for electrons. So there's brilliant for nucleophilic attacks. Now, if any of you are chemists here, what you might notice are these are sort of funny looking hydrogen atoms which are divalent. They've got two little bonds. Well, they're bridging hydrogens. In fact, this hydrogen is sharing two electrons with this boron atom and this boron atom in a triangle. It's delocalized. And so these hydrogens are very acidic. You can deprotonate them easily. And so you can deprotonate those hydrogens, and then afterwards you can insert different atoms into that cluster. So there's lots of things you can do as a chemist. Okay, you can whack it, you can do all sorts of interesting, fantastic chemistry. You can add atoms into the cluster, take atoms out, you can change the periphery of the compound, I can put different groups in different positions, and I can control that depending on my understanding of the chemistry and how it works with the the degree of electron-rich areas of the cluster. However, I want to tell you about the real rock star of boron hydrochemistry, and my favourite molecule, and the molecule I know most about, and this is B18H22. Now this molecule is essentially two of those decaboranes, and they're fused together, and they share two atoms of boron. Okay? Now this molecule is incredible. So this molecule was first made by Frederick Hawthorne. He's an American chemist. He's probably in the run for a Nobel Prize, and all his life he worked with the boranes. And the structure was first elucidated, was the atomic structure, the molecular structure rather, was first elucidated by Lipscomb, who later won a Nobel Prize for his work on the boranes. Now, I started working with this compound when looking into its use in the fabrication of semiconductors. So semiconductors, which are the basic unit of all our electrical devices, are, this is where I apologise if I'm insulting anybody's intelligence with my descriptions. I don't know whether you're chemists or not. Okay. So semiconductors are essentially chips of silicon. So you've heard of silicon chips, you've heard of Silicon Valley. So that's because it's based on silicon. And it's crystalline silicon. So the atoms of silicon are in regular arrays, right? So there's lots of atoms in arrays of this silicon. Now silicon by itself is very boring, it can't do anything. In fact, it's an insulator. It won't carry any electrical charge. But if you dope a bit of boron into the silicon, some atoms of boron will enter into places where the silicon would exist. And as boron has one electron less than silicon, it forms these little electron holes, through which electrical charge, electrons, can move. And so if I connect it to a voltage, you'll get a weak semiconductance, so a small flow of electrons. Now, by itself that's not particularly interesting, but if you then put in close proximity another semiconductor, also made of silicon, but doped not with boron but with phosphorus, which has one electron more than silicon, then you've got two plates which you can put close together, one of which has got a few extra electrons, and the other's got electron holes. And if you apply a voltage, a current will flow only in one direction, and only ever in one direction. And that allows for the 0101 binary bit, how the computers work, right? Anyway, I started, when I finished my PhD was about, developing new routes to big cluster molecules like B18, H22. And my work at the beginning was using these compounds to dope into silicon to form these silicon chips with very shallow implants. Because if you can imagine any device, you can shorten in 3 dimensions. And the shorter the passage an electron has to move, the faster the device is. So we had some success there. And but that's a long story. But we had some success there. You can imagine I was working this compound on its use in the fabrication of semiconductors. A lot of this work was done with an American company called Semiquip. So I was traveling a lot from here in Liège. Every 3rd week I had to be in America, and we were developing this new system. During this time, I recognized one day a surprise glasnost property. Thank you. So a surprise property of this compound. And this is it. here I've got a gin, well, a whiskey glass, and into it I poured a solution of B18H22, which is colourless. And I was working with it in my laboratory by the window one day, and I noticed this colourless solution was, beginning to fluoresce a blue colour. When looking into it properly, if I actually hit it now with a laser, a UV laser, you can see this wonderful blue fluorescence. And here's that sort of work on a graph, right? So the black curve here, this is the absorption. So a molecule, if placed if you shine light on the molecule, it will absorb something. And here's the wavelengths of absorption. So this is the wavelength. If you remember, blue light begins at we can see from 400 to 800. Blue light, green light, orange, red. And this is UV. So I noticed that if you hit it with UV light, this molecule that I've been using for the fabrication of p-type semiconductors had this wonderful property of that it was able to convert UV radiation into blue light. So I became interested in that to a large degree. It's the first borane compound that had this property of fluorescence, so I thought it'd be worthwhile to look deeper into it. So I began to research on that. Now, this is I don't want to get it too complicated, but this is called a potential hypersurface. This is what's going on when it's absorbing and emitting light. So your molecule of B18, this is its ground state. Okay? So this is when it's in its normal, and it's vibrating normally, normal movement. Okay? And if you get the wavelength correct, it will absorb that UV light and it will promote itself to what's called an excited state, where the molecule is sort of excited. And this excited state is metastable, it's a little bit stable. So you've got this little well of stability here. This is the excited state minimum, where it can, it does this thing, it's excited for a while. But molecules are like men. You can be excited, you can get into an excited state, but that excited state is temporary. And sooner or later you have to return to the ground state. It applies for us, it applies for molecules. So this molecule's excited, it's excited for a while, and then it returns down by emitting a photon of blue light. Now, what's important here though, is that there's several options for an excited molecule and what to do when in the excited state. Most molecules if you excite with UV light, they become excited and then they reach this, what's called a conical intersection point. They can go down like a ski slope, back down to the ground state, just by vibrating the energy off. And B18 though, our molecule, has a big energy gap between this excited state minimum and the conical intersection point, and it's very difficult for it to climb over that. So it stays excited for a long, long, long time. And here you can see it. Oops. This is in picoseconds, very short time scale. But here's the point of excitation. This is when the molecule absorbs the UV light. And then this is a general normal molecule. The molecule absorbs the light, becomes excited, and very quickly releases that energy just from shaking it off. But our B18 molecule stays excited and excited and stays excited, and it keeps being excited for a long, long, long time. 11.2 nanoseconds, which is, of course, not a long time not for us, but that's a long time for a molecule. And during that period of being excited for that long time, and then it can't get up there, it gets frustrated to be able to get to the top, so therefore it releases its light as blue energy. I'm going to skip through this because I'm going to run out of time. Now, a bit later on, I just skipped through because, well, let me just go back one thing. This is what's called the quantum yield, okay, 97%. This means that for every 100 photons it absorbs of UV energy, 97 photons are emitted as blue light. So it's the efficiency of that fluorescence, efficiency of the emission. And 97% is huge. Very, 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 we were thoroughly surprised. This was extremely encouraging when we found out we had this really efficient emitter. Now, I did about a decade's work working out what happens in the 3% of the time that it doesn't fluoresce, but I'll have to tell you that maybe next year. But with this extremely long lifetime of being excited, and its extremely high efficiency of production of light, then it turned out this molecule became a very good candidate, and indeed the first ever boron laser. So we found that, because the difference between a laser and just a normal luminescent species is that in this system here, if you imagine it not just for one molecule, but many, many, many billions and billions of molecules in your sample, and at any point you consider the population of molecules in the ground state and the population of molecules in the excited state, if you can get more molecules excited at any one moment than in the ground state, you can get an amplification of that energy, and that's the laser output. And because of the extremely long lifetime of that excited state of this molecule, we are able to, so here you can see we're pumping with energy, where you can imagine a big population here. We begin pumping with energy, pump, 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 pump with UV lights here, pump, 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 and then all of a sudden at this point, at about 115 microjoules of energy, then there's more excited molecules at any one moment than in the ground state, and that's when we get an amplification of the energy in this laser emission from our boron laser, making it the first boron laser. And interestingly as well, is if you're trying to sell a laser, if you want to buy a laser, there's two important things. First of all, the laser efficiency, so how efficient is it? And secondly, its photostability. That means how long can you use it until entropy kills the molecule, until the molecule falls apart. So every molecule will eventually just fall apart because it's going through so many billions and billions of cycles every second. And we found that this is a test of photostability with lots of other blue emitting laser dyes, and ours competes very, very well. But I'm going to finish with briefly what we're working on at the moment. That was a story about our discovery of the first boron laser. But this same molecule, so if you can imagine, I've essentially for 26 years, I've focused on this one particular molecule, from which you can fabricate P-type semiconductors. You can generate laser light from, and now we're using the same molecule in our new European project into seeing whether we can use it as a suitable target for boron-proton fusion. So the concept here is that you've probably heard in the news quite a lot at the moment about nuclear fusion as a source of energy. Yeah? Now, most of that work is based on the fusion of deuterium with tritium. So these are heavy isotopes of hydrogen in something similar to what our sun does. But it's not the only fusion possibility. Now, most of the work has been done on deuterium-tritium fusion because this is the nuclear fusion reaction that has the lowest threshold. It means the fusion reaction begins at the smallest amount of inputted energy. But there's problems with this form of this fusion because it produces ionizing energy in forms of neutrons, and also it's very difficult to source tritium. Whereas there's other possibilities such as the use of boron-proton fusion. So we can, I'm just coming to the end, we can...
I just forgot to do this virus.
Yeah, I know.
What do you know that we
I'm on my last minute. So the idea, we're using our boron material, we're hitting with incredible, these are the facilities. This is in Larvi, in Praha 8, and they have one of the most powerful lasers in the world. It has an intensity, it's a 550 joule laser, which is massive, okay? So it produces about 30 petawatts per centimetre squared. What does that mean? It means it's 200 times 10 to the 15 times more energy than what the sun, the sun rays that hit our planet per centimetre cube. So it's a huge amount of light energy. And the idea is that in this reaction chamber here, we place our molecules of B18H22 in a specially made target sample, and we hit it with light of this sort of energy from different directions. And we thus confine this boron hydride material entrapped in multi-directional light. And so the boron hydride has got nowhere to go. And we increase the intensity of that light until the target has so much energy that it can overcome the normal barriers to fusion, and the protons begin to fuse with the nuclei of boron, and it forms alpha particles, which are a source of clean and cheap electrical energy. So, with that, thank you for the invitation. Thank you for your kind attention. These are just some of the names of people who played a key role in some of the work I mentioned, and I'm happy to answer any question in Czech or English, if you wish. Thank you.